You ready? Horizontal circles. Oh, and the next lesson is going to be vertical circles. But this is when we're going to start to apply this, keeping in mind our circular acceleration equation is v squared over r, or 4 pi squared r over t squared. Those are all ways to calculate acceleration. First of all, some conceptual stuff. Imagine that you're in a car turning a corner, like in the picture. What's the direction of your acceleration? And what's the direction of the force that acts on you? So the key idea, if you're moving in a circle, like that, which way are you accelerating? Who remembers? Towards the middle. So you know what? Let's go yes, yes, no, no. You're not accelerating outwards, which many people will tell you, no, that's your own inertia, and it's not outwards. What direction is the force? Why must it be inwards? Well, if F equals ma, you know what? A is the vector which gives force its vector. So if your acceleration is inwards, your force is inwards. Yes, no, yes, no. By the way, if you don't use this method to answer, because you've noticed on the test there's lots of 2-column questions like this. This is how I always do this, because by doing this, rather than having to figure out what the correct answer is, now I just zoom out. What is the correct answer? The only one that's got 2 check marks on it. What direction is your velocity? Tangent to the radius. That'd be your velocity. But your force and your acceleration are towards the center. It says explain your answer using relevant physics principles. You know what? We did that vector subtraction proof in lesson 1, so I'm not going to bother re-explaining it, but we did a lovely vector subtraction and saw that it did end up pointing towards the center. In Latin, the word centripetal means towards the center. So when an object is moving in circular motion, it has a, here's your word of the day, centripetal acceleration. By Newton's second law, first law, there must be, you know what, I'll give you second law. You can, first or second works there. By Newton's second law, there must be an unbalanced force in the same direction as the acceleration. What they're really saying is F equals ma, the F direction comes from the a, because m's a scalar. So an object moving in a circle has an inwards centripetal net unbalanced force. Some, me, like to use the following notation. I use AC for circular or centripetal acceleration, FC for circular or centripetal force. C means centripetal, but you can just remember, Jason, circular, because that's the path you're tracing out, and that's what most kids remember for C. Handy, important note. Here's what this means then. In our winner minus loser approach, remember that? The centripetal force will always be the FC will not actually appear on the free body diagram. FC will not show up on the free body diagram. The same way as F net never showed up on the free body diagram. The winners and the losers did, and it was when you combined them that gave you F net. Let's try one. Example 1. I like example 1, I like example 1, I like example 1. And it's useful. Car is approaching a circular turn that has a radius of 60 meters. If the coefficient of friction between the car and the pavement is 0.45, what is the maximum speed that the car can safely travel through the turn? Really? We can solve this? Easily. Easily. This is a job for a free body diagram. Let's have the corner go, sure, this way. The car's going around the corner this way. Here's the car. What are the forces acting on the car? Get the obvious one. You know what? That's really tough to show. Let's draw a side view picture as well. So here's the side view. In fact, really, instead of side, let's say front view. So here's the pavement. Here's the car. Here's the headlights facing me. There's one tire. There's another tire. So it's coming towards us out of the page. And to show that, I'm going to say, here's the center of the circle, and we're going around it that way. The same way we're going around the circle this way. These are tough to draw, Mitchell, because it's a three-dimensional situation. Usually I'll draw the side view free body diagram from now on, but just to walk you through it. What are the forces acting on the car? Get the obvious one. Gravity. So I'm definitely going to have mg down. That's really tough to draw on the top view because it would be into the page. Whatever. Is the car sinking into the ground like quicksand? Is it flying into the air like Superman? Hey, what do I call that force there? Also tough to draw. You can imagine an arrow right here pointing out of the page at us. A little tricky to draw. What else? Here's the key. What path is this car tracing out? A circle. So where must there be an unbalanced force pointing? Toward the? So there has to be a force pointing this way. There has to be a force pointing this way. Which force? Not FC. Does not appear on my free body diagram. What force pushes a car around in a circle? And your hint is, why is it tough to corner on ice? It's friction. That mystery force, the force that's pushing me in a circle, is friction. You okay with that, Manny? Okay. I mean, you have to do some thinking to get there, but hopefully you're like, oh yeah, that makes sense. Vertically, in this picture right here. Oh yes. Pardon me? The tires are applying a force against the road, but that's forces on the road. I'm drawing the forces on the car itself. So it is true. The friction that we're getting there, that tire is pushing against the road, but the road is pushing on the car with friction, and I'm drawing the forces on the car, not the road. Okay? It is like forces come in pairs, but I'm not drawing all the pairs. I'm only drawing the forces on one object. Who's winning? Vertically in this diagram, it's a tie. Is the car sinking into the ground like quicksand? Is it flying into like Superman? Centripetally, or I'll say horizontally because it is a horizontal circle. Who's winning? Well, there's only one force horizontally. Which force? Okay, so here's how we solve this. Winner. Is there a loser? No. What path are we tracing out? Here's the difference. Equals FC, because we're moving in a circle. Not FNAT, not MA, FC. Friction equals MAC. Because that's still MA, but moving in a circle. There's two equations for the acceleration. This one or this one. Which one do I want to use? What's this question asking me to find? Oh, I think I want to use the one that's got a speed in it. If this question asked how long to go around the corner, how many seconds, I'd use the one that's got a time in it. Is that okay? So, I'm going to argue v squared over r. Now, the rest hasn't changed. Friction is what times what? I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Looking at my lovely free body diagram, the front view one in particular, which force is the same size as the normal force? So I get mu mg equals mv squared over r. Hey! Are you saying that semi-trucks and little Austin Coopers can drive on the same roads? Really? The mass cancels. Now, they can't, by the way, they can't always do the same corners, but that's not because of this. That's because the trucks are so big with the trailers, they just can't physically make it around the corner, which is why they give them the outside lane all the time at left turn signals and things. That's a physical issue, not a physics issue. What are we trying to find? Oh, how would I get the v by itself? Times by r, and that'll give me v squared. Oh. So you're saying v is going to be mu g r square root? What's mu? I don't know. What's mu with you? Or did they give it to me? What'd they say mu was? 0.45. G has been 9.8 since Physics 11, and they told me the radius, yes? This is, by the way, if you ever wonder, how do they calculate speed limits going around corners? You've seen the signs. Here it is. What was the radius? 60? The maximum safe speed (16.3 meters per second). Now that's the maximum safe speed. In fact, if you were doing exactly that, you would feel very uncomfortable driving. You would feel like your car was just about to slide off the road. Okay? So in real life, if this was the corner, we'd probably drop it to like 9 meters per second and then convert that to kilometers per hour, and that would be the speed limit sign that you would see. The other thing that we would do, which we're not going to get into now, we would bank the corner. But that brings in inclines and ramps. We may look at that later, but today is horizontal circles. Okay? You can expect to be able to, or be asked to analyze a car going around a corner, because there's some beautiful physics going on here. Example 2, a test tube rotates with a period of 9.9 times 10 to the negative 4 seconds. What's the centripetal force on a 1.8 times 10 to the negative 9 amoeba at the bottom of the test tube? The bottom of the test tube rotates in a circle with radius of 0.15 meters. Clay, what's this question asking me to find? Centripetal force? Centrifugal is a fictitious, not a force, it's inertia. Okay. Centripetal. 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 Okay. Well, I'm not going to do a free body diagram since it's actually wanting me to calculate the force. I'm just going to say it's FC is MAC. Did they give me V, the speed, in this question? No. Did they give me the period, how long to go around once in seconds in this question? So I'm going to use m 4 pi squared r over t squared, the other version of acceleration from my formula sheet. So how do you know which one to use? Depends on what they gave you or what they're asking. Did they give me the mass, m? Yeah. Did they give me r, the radius? 0.15. Did they give me the period? I'm going to ask everybody, try this on your calculator, because many of you are going to get an error, and you want to find out now. So get your calculator out. Some of you, this will work. Some of you will get an error. Anybody get the error? No one yet? As an answer, you should get 0.010875. That there. I think. Let me double check. No typos. Good, 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 good. Divided by. Good. If you didn't get that, now's the chance to figure it out. Where you might get the error, some of your calculators might not let you go pi squared. They might make you type pi times pi. Some will. Most will. But some won't let you do that. If you're not getting that, you might want to give me a holler. And don't clear your calculator. What was the answer to that question? How about 1.09 times 10 to the negative 2? Newtons. It's a force. Is that okay? Turn the page. Quick look at money. The wave swinger, an empty swing on an amusement park ride, has a mass of 10 kilograms. If the swing has a kinetic energy of 460 joules, what's the centripetal force on the swing? This question wants me to find that, which is going to be that. Now, it's either going to be, don't write this next bit down, m4 pi squared r over, don't write that down, or it's going to be mv squared over r. Which one of those am I going to use? The one with the T or the one with the V? Why? Clay, you're correct. How come?
Because you need kinetic energy. Like that.
Kevin, what?
Because of the kinetic energy.
They gave me kinetic energy. If I know the kinetic energy, I can find V. If they had given me some other information, maybe I could find time. But in this case, so let me erase this. And you all can now write this down. We're going to use Fc equals mv squared over r, where m is 10. What else did they tell me? They gave me the Ke, which is a half mv squared. Right? You know what? Just for giggles, let's do this all algebraically. Let's not put in any numbers yet. Let's get the v squared by itself. How? What will I do with the m? How will I move this m over? Divide? What about this 1? Who cares? What about this 2 on the bottom? Raj? Okay, you know what? I think I actually have this then. 2 Ke over m equals v squared. Now, I was going to say, how do I get rid of a squared square root? But I stopped because actually, don't I have a v squared on the other side there? In other words, Vikas, can you read this to me? V squared equals what? V squared equals what? Wherever I see a v squared, what can I write? When I see a v squared, what can I replace it with? When I see this v squared, what can I replace it with? Oh, kind of clever. Let's do that. I always like it when I can substitute things indirectly. So there's going to be an m, there's going to be an r, and then there's going to be a 2, a Ke, and an m. Is that okay, Amelia? Kind of cool. Oh, I also noticed something else quite convenient. Do I know KE? Do I know R? From the picture. If they hadn't given me the picture, I couldn't solve this, but okay. Plug and chug, complicated plug and chug, but plug and chug. 2 times 460 divided by 7. Cool. You know what? 131 newtons. I'll go to 3 sig figs. By the way, Mitchell, I could have actually solved for V over here and then kept that as an answer button on my calculator, and then over here gone mv squared over r, but I just thought it was kind of cool that I could substitute a whole expression in and stuff canceled. And I'm a math nerd, Trav. I always like it when stuff cancels. I like it when an expression that originally looks ugly turns out to look okay. Sort of like if you got a haircut. Okay?
Oh my God.
Here we go. Example 4. A car can travel without slipping at a maximum speed of 32 meters per second in a circular path of that on a dry horizontal surface. When it rains, the coefficient of friction is reduced to 1/2 of its original value. What's the maximum safe speed of the car under this wet condition? Oh, let's do some road safety. Dustin, it seems to me this question has 2 parts, dry and raining. So you know what? I'm going to be clever. Okay. If I'm drawing a free body diagram, an FBD, if I'm drawing a free body diagram, it seems to me that, again, if I do the front view, so here's the car, there's the tires, yeah, it gets worse, there's the front lights, and it's going around the corner, let's say like this. By the way, I'm just drawing that, Mitchell, so we have the same frame of reference is all. What are the forces acting on it? Get the obvious one. What else? Normal force. And then the key thing to remember that we proved earlier, when you're going around a corner, what force is pushing you in a circle? Okay. It'll be the same free body diagram whether you're dry or raining. So let's go walk over here where it's raining. We would say this. Friction is what's pushing me in a circle. Jason, when you're done yawning, what's this question asked me to find? I think I want to use the acceleration with the v in it since it's asking for speed. I think that v is what we're going to end up finding. So I'm going to go like this. mv squared over r. By the way, common mistake, can everybody look up? I see kids do this all the time. Because that's A. But force is not acceleration. Force is mass times acceleration. On your formula sheet, all they give you are the acceleration equations. They expect you to clue in to make it a force, times it by the mass. Friction is what times what? I don't know the normal force. Oh, but look. I know the force is the same size as the normal force. So I end up with this. Mu mg equals mv squared over r. Yay. You know what? I end up with the same expression we did in our first example. I end up with the maximum safe speed is mu times grr square rooted. Okay. Do I know r, the radius? Yeah. Do I know G? 9.8. Oh, what don't I know? I bet you I'll find that when it's dry. And then it says when it's raining, mu drops to 1/2. Oh, I'll just divide it by 2. So now, Dustin, let's go walking over here when it's dry. When it's dry, we have friction pushing us around in a circle. Mu times the normal force equals mv squared over r. Don't forget to times by m to make it a force. I don't know the normal force. Oh, but look. I know, oh, Mr. Duick, this seems really repetitive. Well, so far. Except, what do I want to find here? What's mu? I don't know. What's mu with you? How would I get the mu by itself? Now, this is mu dry. How can I make that mu raining? You know what? I'm going to, again, because I'm for some reason in an algebraic mood, I'm just going to say like this. Mu rain is going to be v squared over 2gr. Yes? Also, because I'm looking at this, I think a lot of cool stuff is going to cancel, which I always like. I'm a bit of a math nerd. I like it when something ugly becomes something clean. Sort of like when, never said that already. Mr. Duick, have you been holding on to that joke for like quite a while? So let's see. It's going to be a v squared, and on the bottom a 2gr. There's mu. And then the g and the r just drop down. Oh, you know what? We got 2 v's. This is v dry. What's kind of cool here? What we're actually finding is a universal driving condition. What happens to the G's? What happens to the R's? In fact, what we're finding is, hey, when it's raining, this is what your speed needs to be adjusted to no matter what. Oh, okay. On any planet, for any radius. What was V dry? By the way, if you even want to go further algebraically, Kyle, what's sitting right there? Inside of a great big... Really, we end up with this. Your dry speed divided by root 2. That's the factor. You slowed down by a factor of root 2, which I would not have spotted coming, but kind of cool. That's if mu is half. What if mu is 1/3? Turns out you slowed down by a factor of root 3. What if mu is 1/4? You slowed down by a factor of root 4. What if mu is 1/8? You slow down by a factor of root 8. This is the universal drive. If you're wondering how they come up with these driving restrictions and road signs and speed limits, I'm sure that's somewhere in the RCMP handbook or the engineer's handbook for creating roads. What was V dry? It did tell you, didn't it? 32? $22.6, is that right? By the way, Raj, if I wanted to make this question more terrifying, I wouldn't have given you the radius, which would have freaked some kids out. But do you notice we never actually used the radius at the very end? 22.6 meters per second, because it's a velocity. Speed. Josh, here's your answer. A technical comment on turning. The reason that friction is inwards has to do with how wheels work. Oh, looks like I'm crossing it out. Has to do with how wheels work. When we turn our front wheels, our car wants to keep going in a straight line. The wheels apply a force against the pavement in that direction because our car wants to keep going in a straight line. The pavement friction applies a force on the car in that direction, and that's what makes you turn around in a corner. That's the Newton's third law, reactive force. But because this force here is on the road, not on the car, I never bothered drawing in my free body diagram. What do I care? We can. If we have a big enough, if we have sticky enough tires, we can turn sharper. In other words, if mu is bigger, this force is bigger, and I can corner better. Okay. By the way, also, we're simplifying things because we're treating the car like a dot. In real life, wider axles also help you turn better. Lower center of mass helps you turn better. So we're going to a simplified case. That is true as well. Yeah.
What if you're a rear wheel steer?
What if you were rear wheel steer?
Yeah.
This is why when you're driving in reverse, you seem to turn so much sharper, right? Or if you've ever anybody driven a forklift, because forklifts are all rear wheel steer. Yeah. It's a very, very different way of steering. Okay. There, rather than having friction, rather than your front tires applying a force, friction putting you in a corner, instead your back tires apply a small force of friction to swing the back end around and rechannel your inertia. But you can certainly turn or corner sharper that way. In fact, you're much more likely to oversteer and spin out than you are going forwards. Is that okay? Hey, another way you could do, another use for horizontal circles, artificial gravity, which I hope, Kiowa, happens in your lifetime. I would love it if you guys got to see part of the big spaceship Star Trek universe heading up. I would love it if in your lifetime the solar system was explored. That's doable by the year 2100. And by explored, I mean people visiting other planets, not just the moon. Pardon me? In your lifetime, that's doable by the year 2100, and some of you guys will still be kicking around. Nah, you might be alive. You might, because lifespans are getting better. We'll see. One method for doing that, because a lot of these journeys would take several months, would be to create artificial gravity. How? By building a circular space station and spinning it. So I have both a side view and a top view. Let's look at the top view. Here's our person. What are the forces acting on this person? Why can't I say get the obvious one? We're in space. Okay. But what path is this person tracing out? So there has to be a force inwards. Has to be. What's pushing him inwards? And your hint is just tilt your perception sideways. You're standing on a floor. It's a normal force. Now, some problems with this, because your circle is not very large, probably there would be a different velocity with your head than with your feet. You would feel like if you were walking in the same direction as the space station was spinning, like your head was always wanting to fall back and be left behind, and you'd have to learn to compensate. There might be some dizziness, some inner ear vertical. You'd have to get used to that. But The positive is stuff would sit on tables. I was watching an interview with Chris Hadfield the other day, and he was commenting that when he came back from the International Space Station, it didn't happen to him. When they got back, they were having their first meal, and one of the other astronauts very absent-mindedly put a glass to rest in midair and let go of it because he was so used to being able to do that. And literally, as he did that, So, we like stuff to stay where it is on tables and things. So we could do this. In fact, our equation here would be normal force is equal to centripetal force, is what's pushing me in a circle. So, example A. If this space station has a radius of 35 meters, what does the period of rotation need to be for an astronaut to experience 80% of the Earth's gravitational field? Normal force is what's pushing me in a circle. It wouldn't, no, it wouldn't, because it would still already be moving with you, so it would have a tangent velocity. It would already have been changing direction as soon as you let it go. Now, what would happen then if you dropped something? It would fall like this, but you would be spinning, so to you, it would appear as though it fell straight down because you're moving. You wouldn't notice that it had moved sideways because you're moving sideways along with it. It would work, right? So if you drop something, right now, because it's spinning, the object that you're holding has a tangent to the radius velocity. Yes? Newton's first law says it's going to keep going in this direction at a straight line at a steady speed when you let go of it. But you're going to spin into it. It's going to hit the ground by your feet, and you'll think, oh, it fell straight down because you're in an enclosed space station. You can't see outside. So as far as you're concerned, it looked to you like it went straight down. You can't tell. Because it's going to go in a straight line at a steady speed, and you've spun. Pardon me? But you're touching the floor. You asked, what if things aren't touching the floor? Because you're touching the floor, there would also have to be some friction to keep you moving sideways. Yes. I'm ignoring that right now. Yeah, you are. There's a normal force. No, there's no gravity. You are. You have to be because you're moving in a circle. There has to be an unbalanced force pointing towards the center. Has to be. That's the definition of moving in a circle. Come back to that, okay? Let me see if I can convince you. You had a question.
Do we get to watch the 2001 Space Odyssey
No,
now?
but that's a great movie with some pretty good physics. The only problem there's some issues with that circle that they do as well. In particular, if you run the numbers, the guy that's jogging, that scene, he would actually be feeling like his head was being left way behind because that radius isn't very large. But we'll come back to that. Let's continue with this. By the way, am I going to use this one? Or I'm going to use this one for FC? Am I going to use this one? Or am I going to use this one? Why the second one? They want me to find the period? I better use the equation that's got the period in it. Says the people that have done the homework. If you haven't done the homework, you're going to be going, what is that second one? Should have done lesson 1. Okay? So I'm going to say this is going to be m4 pi squared r over t squared. What about here? I don't know the normal force. Oh, but look. The question has told me how big I want the normal force to be. 0.8 mg, 80% of Earth. Will spinning a space station produce gravity for a little child as well as for an adult? Why? Like that. What does this question want me to find? T. How would I get the t by itself? Well, it's on the bottom. See it? I'm going to first of all move it to the top. Stuff moves diagonally. So I'm going to say to myself, t squared equals, and then I'm going to have the 4, the pi squared, the r drop down, and I guess the 0.8 g would move to the bottom. Is that okay, Dustin? And how do I get rid of a squared? Okay. If I want 80% of Earth's gravity, and the space station that we built has a diameter of 70 meters, a radius of 30 meters, it needs to spin every how many seconds? 4 pi squared 35 divided by 0.8 times 9.8 square root. 4 pi squared times 35 divided by bracket 0.8 times 9.8 square root. This needs to spin every 13.2 seconds. 13.3 seconds, sorry, round off properly. That would make you feel 80% of your weight. Your mass wouldn't have changed. Remember, weight is the mg. The artificial mg would be 80% of it. Is that okay? We'll come back to some of the hypothetical, and I got some videos to show you as well. But I want to get through the lesson because you guys got a week off. What's the frequency of rotation? How many hertz? Who remembers how period and frequency are related? They are. The frequency is 1 over the period. So literally, oh, you know what? Mr. Dewick, is that why we actually have a reciprocal button on our calculator? Yeah! You do, if you go look. You've got a little to the negative, x to the negative 1 button. So if you have the answer, and then just hit the little x to the negative 1, it'll take the reciprocal. 0.0753 hertz. .0753 hertz. Very low frequency. Yes? Time, seconds. Period is how many seconds to go around once. It will take 13.3 seconds to go around once. That's what the period is. I could also find how fast the space station is spinning. Didn't bother. Or maybe I did on the next page. Oh, here we go. Suppose an astronaut begins to climb a ladder. This goes back to your point, Clay. That leads to the center of the space station. As the radius gets smaller and smaller, he will feel lighter and lighter and lighter and lighter. At what radius will he feel 30% of his weight? Okay. Well, the fake gravity, normal force, is being caused by the fact that we're spinning in a circle. Yes? I don't know the normal force. Oh, but look. They told me that they want the normal force to be 30% of mg. And that equals m4 pi squared r over t squared. By the way, I went with that one because I found t, and I have a feeling I'm probably going to need to use it. So if we did design a rotating space station, there would probably be like spokes, and each of those spokes would have a ladder that you could climb. In the very center, there'd be an axis where things would be weightless, where the normal force would be 0. You might make it a recreation center. Go fly around for a while, maybe. Or you might what would be pretty cool is if you lined that axis with a swimming pool, because you would have a completely cylindrical pool with air down the center, and maybe you could climb down the middle and then dive into the pool if you gave yourself a big push, because if you gave yourself a big push, your radius would be slowly moving away from the center. Gravity would slowly increase a little bit, and you would slowly free fall into the pool. That'd be you could do all sorts of neat stuff with this. I hope that happens in your lifetime. That'd be cool. Meanwhile, what are we being asked to find here? Oh, by the way, would this work for a child as well as for a grown-up? Okay. Jordan, what's this question asked? Jason, yeah, I was doing so good. What's this question asking me to find?
The radius.
Oh, let's get the r by itself. I guess I'll divide by 4 pi squared. And I'll times by t squared. Yeah? Okay. By the way, this is why I show this unit is why I've taught you and emphasized the formula manipulation thing so much, because the fact that you guys can see that is such a huge time saver. So you're telling me the r is going to be 0.3 gt squared over 4 pi squared. That would get the r by itself. If you still have this on your calculator, and you want to get the period back, how can I get the period back from this? Take the reciprocal again. There's the period, and I'll use, so for t, I'm going to use my answer button, because, you know, that's the way I roll. In terms of what we're going to type, it's going to be 0.3 times 9.8 times 13.3, but I'm going to use my answer button. Squared all over 4 pi squared. I think I'll need brackets around the bottom. I'll put a bracket around the top. I don't know if I need it or not. By the way, I know the answer is going to be less than 35 meters because that was the radius on the outside. So there is a built-in error check. If I get an answer bigger than 35, I've messed up. Oh, 13.1 meters. 13.125, 13 and an 8, 13.1. Keep climbing, you'll feel lighter. And notice, when r is 0, what does this work out to? If you got a 0 on the top, what's 0 times pi? Times 4? Divided by t, still 0. Oh, you have no normal force. That's where you feel weightless. Dead center, when the radius is 0. Oh, there you go. I didn't know I put that question on there. I remember thinking just now, that would have been a nice question to ask. Scroll ahead, Mr. Dewick. Another classic horizontal circle ride. How many more are we doing? Boy. Oh, okay. Another classic horizontal circle ride is the Gravitron. Gravitron spins people around in a circle. I like this question, I like this question, I like this question. This is a nice question. The Gravitron spins its riders around in a circle. If the ride has a radius of 4.8 meters and it rotates every 2.5 seconds, what's the minimum coefficient of friction required between the riders and the wall of the ride? Any suggestions on how I might do this? You know what this is a job for? Free body diagram. Although, you know what? Since they gave me that lovely picture, I'll label the forces on this person right there. What are the forces acting on this person? Get the obvious one. I got that. Is this person sliding down the wall? No. Is this person sliding up the wall? So there must be an arrow pointing up the same size as gravity. What force is that? I'm not sure. Let's come back to it. What else? Hey, what path is this person tracing out? Leave the headphones off, Kiowa. What path is this person tracing out? So there has to be an unbalanced force pointing towards the, let's do that. What force is that? Fc, Mr. No, Fc does not appear on my free body. It's going to appear in my equation. What force is pushing him in a circle? The wall, which we've called the normal force. You know what? That gives me a hint as to what that upwards force probably is. Ah. Ah. Okay. Well, normal force is what's pushing me in a circle. Am I going to use the circular force equation with the speed in it? Or am I going to use the circular force equation with the period in it? Oh, 2.5 seconds? Okay. By the way, at Playland, it's the period that's the easiest to get because you can get that by timing. To try and get the speed, you need a radar gun or something like that. So that's the one you use the most in real life. M4 pi squared r over t squared. I don't know the normal force. Oh, and I can't say, look, I know another force the same size as the normal force, because I don't. Wait a minute. What other two forces are in my free body diagram? What can you say about mg and friction? They are the same size. You know what? Let's write that over here. Friction equals mg. Friction is what times what? Anyone see it? Huh? I don't know the normal force. Oh, but look. I've got something with a normal force in it. Why don't I get the normal force by itself? How would I get the Fn by itself? So apparently mg over mu. Hey, can little kids and grown-ups go on this ride? Really? How do you know? Well, that's kind of handy. What's this question want me to find? Oh, let's get the mu by itself. Oh, it's on the bottom of a fraction? Oh, wait a minute. Is this one fraction equals one fraction? Stuff moves diagonally. Oh, so if I hear you, you're telling me that the mu will end up here. The g stays where it is. The t squared moves to the top. The 4, the pi squared, and the r all moved. Is that right? Yeah? Oh, God, can you imagine trying to do that by hand? Plug and chug. Complicated plug and chug, but plug and chug. 9.8, what was the period? 2.5? Squared, all over. 4 pi squared. What's the radius of this ride? 4.8 meters. Those numbers are about right, I think. Four pi squared times 4.8. What's the minimum coefficient? By the way, I guess there must be friction for this to work. Needs to be at least 0.32. Stronger would be okay. That wouldn't mean that you would start sliding up. It would just mean that you would really feel like you were being pressed into the rock. You would really feel secure. In fact, if you had exactly that, you'd feel kind of uncomfortable, like you were laying on ice and were ready to slip at any minute. Slip down. Wow, I lost everything. 0.323. I don't know why it does this every so often, but it terrifies me every time. 0.323 units. Okay. Gravitron picture I already showed you. So in horizontal circles, Nick, the vertical forces are balanced. The net force is inwards. It's ma, which is v squared over r, or m4 pi squared r over t squared. And you're not speeding up or slowing down. I'm going to come back to example 7 and example 8, but for starters, you can try number 1. I haven't done an example like that. Number 2 is certainly fair game. Number 3 is certainly fair game. Those are roads. In fact, if you want to, you can prove that for a flat corner, mu times g equals v squared over r. In fact, I think we already did sort of prove that. 5 is fair game. 6 is fair game. 7 is fair game. 8 is fair game. You've assigned everything so far. Oh, I like number 9, the Gravitron, so I like number 10 as well. Spaceship. 11 is good. 12 is good. Holy smokes, you got a week. We won't do a banked corner, though. 14 is okay.